Thanks. Okay,
right.
Thank you.
Second talk, I'll just introduce you. Okay, so second talk will be given by Xiaolei Wu from University of Bielefeld, and he'll be talking about finiteness properties of asymptotic mapping class groups.
Okay, thank you very much for the invitation. It's a great pleasure to give a talk here. So my talk is based on joint work with Javier Aramayona, Kai-Uwe Bux, Jonas, Flechsig, and Nansen, Petrosyan. And I should say I haven't given much talks on online talks. So if I go too quickly, you should let me know. And if you have any questions, feel free to interrupt me at any time you want. Okay. And I hope at the end you can learn something at least. So you probably are familiar with mapping class group, but asymptotic mapping class groups, you probably never hear this before. So I will just starting by introduce what these things are step by step, starting from mapping class group. So mapping class group, so give me a surface, possibly with boundary, possibly with punctures. We define the mapping class group as the isotopic classes of orientation preserving homomorphisms, which fix the boundary pointwise. In other words, it's just pi zero of this homomorphism group, right? And in our case, the surface we're interested in is going to be mostly infinite type surface, but we'll get into that. So there's two subgroups of mapping class group we're interested in. The first one is called the pure mapping class group. These are just the mapping class which fix the ends pointwise, or the you might have punctures. You fix the punctures pointwise. Remember, the mapping class group, the homomorphism has to fix the boundary pointwise, but does not need to fix the puncture pointwise. So the pure mapping class group just those things which fix the ends pointwise. Yeah, and there's another group called the mapping class group of as with compact support. You just taking those homomorphisms which has compact support, literally, yeah. The name suggests the definition. And this because if you have a compact support, then the support will lie in some compact surface, right? And outside is identity. So the pure mapping class group of compact support can actually be understood as the union of countable many mapping class group of finite type surface. In particular, this will be a finite group. This will be a countable group. And the surface we're interested in is some Cantor tree-like surface. Okay, the first one is the so-called Cantor tree surface, which is the genus zero sphere. It's just the genus zero surface or the sphere minus a copy of Cantor set. And second class, you can do the same. You're taking a genus G surface, deleting a copy of Cantor set. Okay, and then you could have also an infinite genus version, which is called the blooming Cantor tree surface, which on the right-hand side, there's a picture joined. So it also has ends as a copy of Cantor set, but all the ends are accumulated by genus, right? It has infinite many genus. Of course, if you erase all the holes, this will also give you, it just gives you the surface, the sphere minus Cantor set, which is the first surface. And if you want, you can also add in some genus at the beginning. So you're getting the second type surface SG minus a copy of Cantor set, right? So for all these kind of surface, we have a short exact sequence. So you have the mapping class group of this Cantor tree-like surface, and it maps into the homomorphism of the Cantor set because this is the ends. Any mapping class group, any homomorphism will induce a homomorphism on the ends, and the kernel has to fix the ends pointwise. So that is the pure mapping class group. And its x-axis is not very hard to show. All these three groups are quite large because they are actually uncountable. You can prove it, but you have to think a little bit. It's not too hard. But as geometric group theorists, quite often we're interested in countable groups or groups with interesting finiteness properties, right? So so maybe this group is too large. So we do know that the homomorphism of Cantor set has interesting subgroups. For example, the Thompson group V. Okay. And this sits inside the homomorphism of the Cantor set. Actually, it is dense inside it. And we know it's type F infinity. And the pure mapping class group with compact support is also countable. So maybe one can build a mapping class group version of the Thompson group and with good finiteness property, right? Okay. Is there any questions so far? Okay, if not, let me just continue by saying what is Thompson group, just in case you didn't know. So the Thompson group V, I want to first introduce using the tree diagram. So an element in V is a paired tree diagram. So you have two trees, T1, T2, where T1 and T2 are finite root binary trees with the same number of leaves, and sigma is a bijection between the leaves from T1 of T2. So in here, I draw two pictures. Both of them have 3 leaves. So to make the element in the Thompson group, I should tell you where the leaves are mapped to. So I label them 1, 2, 3. And on the right-hand side, I need to tell where the leaves are mapped to. Say, I'm just choosing a random choice. And then this will give you an element in the Thompson group, right? Of course, this is not enough because in order to make it a group, you have to have a way to do multiplication. And for that, we need a equivalence relation. And that is very easy. What you can do is you can expand a tree or attaching a caret to a leaf. For example, you can do it on the first leaf and you do on both of them. And then you just map the left leaf to the left leaf and the right leaf to the right leaf. Okay. So you just declare these two tree diagram are the same. Of course, you can expand many times, and then that will give you, the equivalence class can be large. And now you can do multiplication because if you're having two elements, T1 sigma T2 and T2 sigma T3, where these two trees are the same, then you can do it directly T1 sigma prime T3, right? But if these two trees are different, what you can do is trying to using the equivalence relation and trying to expand it to find a common tree where both of them can sit inside. And then you can do the multiplication using the formula here, okay? Of course, I say that Thompson group is a homomorphism, is a subset of the homomorphism group of the Cantor set. And from this description, you might not see it, but it's actually not too hard to see it because every finite rooted binary tree sits inside an infinite binary tree, right? It's kind of like this and keep on going on. And the ends of it is a copy of Cantor set. And it's same here. Both sides, you have a copy of Cantor set. And when you tell me how the leaves are mapped to, so say 3, 1, 2, and that tells you how the ends are mapped to each other, which in particular gives you an element in the homomorphism of the Cantor set, right? Okay. So now I want to tell you how asymptotic mapping class group are defined. So this will be defined exactly as the Thompson group. So I'm just trying to rebuild everything in the Thompson group. We have this infinite binary tree, and then this finite binary tree, and then I just want to give the surface exactly the same kind of structure. But our surface are called Cantor tree-like surface. So you imagine that there is this kind of structure. So first, so I'll put in a rigid structure on the surface. So what I do is first, both of them is called a rooted binary tree. First, I need a root. So this I'll call a base. So yeah, my picture is using the genus 0 case as an example. And then, you have a root and then you attach a caret to it, right? And then in the surface case, I just attaching pans to it. So I sort of giving the tree a pans decomposition. Okay, and I keep on doing that. Okay. So this is very easy because I sort of draw the surface in a canted tree-like fashion, and then I also need a notion of finite binary tree. So this will be the suited subsurface. What is that? It's just connected union of base with finite many pans. Or let's call it piece. Yeah. So these pans, I'll just call it piece because it actually could be different than just taking a pans. And then, for example, I could take in these pans, these three components, the base and two piece. This will be a suited subsurface, which plays the role of rooted finite binary tree, right? And then I want to tell you, so in the Thompson group case, if you tell one leaf maps to another, that more or less will be clear how, because from point to point, there's just one map, but from loops to loops, so these loops, I will just call them suited loops. Yeah, but from loops to loops, there are many different maps. So what you do, you add in a parameterization of these things. So let's declare this homomorphism or define a homomorphism to all these loops. And then once you know how if you know one suited loop are mapped to another, then the map will be clear using the parameterization. But of course, in the Thompson groups, you also have this expansion rule, which is by attaching a caret. In our case, is attaching a piece or a pans. But the mapping class group of pans is also not unique. So you also need a parameterization map from the pans to all of these pans. Okay. And then the expansion rule will be clear using the parameterization. Okay. So now, with this actual structure on the surface, I can define what is asymptotic mapping class group. So what you do is, again, you're taking a pair of surface diagram with sigma 1 and sigma 2 are suited subsurface. Remember, this plays the rule of finite binary tree, and they have to have the same number of suited loops. And phi is a homomorphism from sigma 1 to sigma 2, which coincides with the parameterization of the suited loops, right? And moreover, you can do the expansion, right? The equivalence relation is using the expansion combined, of course, combined with our parameterization. The expansion will be clear. There will be unique way to expand the map. And then once you have this equivalence relation, and then you can do composition because you can make sure the image and domain surface are the same, and then you can do composition just by literally compose the two maps. Okay. Of course, the picture I draw here is for genus 0 case. You could starting with a genus G surface with one boundary component that will give you the genus G decomposition. And you could also have an infinite genus version. So in that case, you're starting with a disk, and then all the surface, instead of pans, you're taking a 3-hole torus. Okay. And then everything else will be exactly the same. So you can define BG, this group, for all G, actually. And now we have some actual structure. So it's kind of different from Thompson group, because Thompson group is actually not an automorphism of the infinity rooted tree. It's only, it's a quasi-morphism. But in our case, the element in the asymptotic mapping class group actually naturally represents an element in the big mapping class group, in the mapping class group of ambient surface, because you can keep on expanding and then up to expand to the whole surface. And your surface originally is a homomorphism of from sigma 1 to sigma 2. After you expand to the full surface, that just becomes a homomorphism of the canted tree-like surface to itself. Okay. Conversely, you can call an element in the mapping class asymptotic rigid if you can return in the form. That just means this map, all the information is determined by this compact support or by this sigma 1. And outside that, it just naturally extend to the outside, okay? And sigma 1 is going to call the support of F. And why asymptotic mapping class groups? So you have the following short exact sequence. So the group BG will map to the Thompson group V. Sort of, this is very clear because we can map every element. For every element in Thompson group V, we can produce, a tree-like finite type suited subsurface, and then we can produce a homomorphism between them. So this part is clear. And then the kernel, you can see that is a pure mapping class group with compact support. And this sort of answers the question at the beginning. We can actually produce something interesting in the big mapping class group, in the mapping class group of this Cantor tree-like surface. And moreover, when G is finite, so BG contains mapping class group of any compact surface of genus G with boundaries. So this is very nice, but this, all this surface actually just lies in the pure mapping class group with compact support already. So, and that is a subgroup of asymptotic mapping class group. So in some sense, these groups are huge. And in the infinity genus case, it contains a mapping class group of any genus, but of course, it's you also need more boundaries. But anyway, Funar Kapoudjian also showed that this infinite type asymptotic mapping class group, when the genus is infinity, the homology of it actually is the stable homology of mapping class group. So it says that this group is kind of huge in some sense, right? And moreover, Rachel Skipper and I, we showed that the BG, the asymptotic mapping class group in finite genus case is actually dense inside the ambient big mapping class group. So in some sense, we can using this asymptotic mapping class group to approximating the mapping class group of this big surface, okay. And now, of course, because Thompson group V, is known to be type F infinity. So the natural question would be, is the asymptotic mapping class group is BG of type F infinity? So it is known before that B0 is finally presented by Funar Kapoudjian. B infinity is finally generated, and BG is finally presented for any G bigger than 1, smaller than infinity. I should say these 3 papers are also where these 3 groups are introduced. So, but of course, up to this point, before our work, so we know very little, right, about the finiteness property of these groups. So yeah, so our theorem says that these groups are all actually type F infinity for any genus. Okay, so maybe I should mention that should say what is group of type F infinity. It means it has a classified space KG1 with finite many cells in each dimension. Okay, and so how to prove this result? Is the proof it follows the Euro pattern. So you're trying to find a space it acts on, and you need some control over the stabilizers. If the stabilizers are type F, you need the stabilizer to be type F infinity. And then if you're lucky, the action will be co-compact, but not in our case. But if the action is not co-compact, and then you're trying to, there's something called Brown's criteria, which you need to find a filtration of this complex, and then you can, if you can show this filtration is highly connected, then you're also fine. Okay, so that is going to be the approach we're going to take in. So we're going to find some contractable complex where BG acts on, and then we can say something about the action. Okay, so the complex is going to be a geometric realization of some kind of poset. Okay, it's a poset, and this is a variation of the Stein complex. I should say that the complex we're really working on is a subcomplex of this. It's called the Stein-Farley complex. It has a benefit, it has a cube structure, but it's more complicated. So I would just say this first complex we running into. So the poset has elements as equivalence class of with two coordinates. The first coordinate is a suited subsurface sigma, and the second one is a asymptotic rigid map. But here, sigma does not have to be the support of F. Okay, sigma could be any finite type, any suited subsurface. Okay, and then two elements are equivalent if F2 inverse F1, which is asymptotic rigid, and we support sigma 1 and maps sigma 1 to sigma 2. Okay. And the poset relation will be clear. So, it do the same, but now sigma 1 does not need to be equal to sigma 2, but only need to be a subset of sigma 2. Okay. And there's also a natural action. So G acts on sigma F by just acts on the same second component. Okay. And you can show this complex X is contractible by showing that this complex is directed, meaning that for every two elements in the poset, you can find some another element which is bigger than this one. This is not too hard, and of course, and you can analyze the stabilizers. The stabilizers is going to be the mapping class group of some suited subsurface, or it's commensurable. It's a finite index supergroup of this. So, but mapping class group of finite type surface is known to be type F infinity. So in particular, we know the stabilizers are nice. The only bad thing is this action is not co-compact. But there's Brown's criteria, which tells you if it's not co-compact, it's fine, but you need to find some filtration about this. And then if you can say something about the filtration, then you're also fine. So there's a very natural filtration about this complex, which is just the number of boundaries of sigma. So taking an element, you have a function maps to actually the natural numbers. Yeah. It's just taking the number of boundaries, and then you're taking the filtration to be, xi to be the symmetric realization of the subposet with at least I boundaries in sigma. And now you can see that BG is invariant. Invariant is very easy because it remember our group, yeah, acts only on the second. Yeah, the action only acts on the second coordinate, so it does not change the number of boundaries of sigma, so it's invariant. And also you can checking that it's co-compact, which takes a little bit effort. So up to this point, you're almost done, but you still need to show that this filtration is highly connected in some sense. And for that, we use the so-called discrete Moore theory. And then there will be a complex arise in this situation called the dislink. And let me just tell you what is the complex in the infinite genus case. I think it's very interesting. So giving us surface genus G with m boundaries, the three-hole torus complex is defined as follows. So this surface, you should imagine this is just your surface, suited subsurface. Okay, let me just show it. It has G genus, and it's kind of like this, and then have B boundaries. Sorry, and M boundaries, and then a vertex is an isotopic class of embedded three-hole torus. So what is this? It's a curve cutting off a three-hole torus. Genus 1 with two boundaries, and if having two such vertex, that if they are giving you, they need to collect by age. if they're pairwise disjoint up to isotopy. And if you have k plus one of them, if they are pairwise disjoint, then they form a K simplex. So our main technical, actually very hard technical result is we show that this complex is highly connected when M and G are sufficiently large. Okay. And with this, you can show the asymptotic mapping class group of infinite genus R-type F infinity. Okay, I'll stop here. Is there any questions?
Well, any questions? Doesn't seem like it, so let's thank our speaker again. And we will reconvene in 4 minutes.
Okay. I'll stop sharing.